Hello everyone. Today we will explore a fundamental challenge in training a deep neural networks, the vanishing gradient problem. This issue affects how well our models learns, especially in deep architectures and sequential tasks. I am Kalpana S, assistant professor at Shriram Engineering College, and I'll guide you through the causes, consequences and solution to this problem. Let's begin by understanding what gradients are. In neural networks, gradients measure how much the error changes with respect to each weight. During backpropagation, we use these gradients to update weights and improve the model. If gradients are too small or too large, learning becomes inefficient. So, gradients are the lifeblood of learning in deep networks. The vanishing gradient problem occurs when gradients become extremely small as they propagate backward through layers. This is especially common in deep networks using sigmoid or tanh activations. As a result, early layers receive almost no signal to update their weights, leading to poor learning. Think of it like trying to shout through a long tunnel, your voice fades before it reaches the other end. Next, go to mathematical insight. Let's look at the math function. The derivative of sigmoid is sigma x into 1 minus sigma into x, which is always less than 0.25. When we multiply these small values across many layers, the result becomes nearly zero. This is why gradients vanish. It's not just a theoretical issue, it directly affects how well our models train. Difference between vanishing versus exploiting gradients. Here's a comparison. Vanishing gradients shrink and prevent learning, while exploiting gradients grow uncontrollably and establish training. Both are problematic. In vanishing gradients, the model gets stuck and learns very slowly. In exploiting gradients, the model diverges and fails to converge. Next, consequences. What happens when gradients vanish? First, training becomes extremely slow. Second, the model may get stuck in poor local minima. Third, in sequence models like RNNs, the network fails to learn long-term dependencies. This is why early RNNs struggled with tasks like language modeling or time series forecasting. Next, we see the solution to the vanishing gradient problem. Fortunately, we have solutions. Rectified linear unit activation avoids small gradients. Better weight initialization like Xavier or he helps maintain gradient flow. Batch normalization stabilizes activations. Residual connections allow gradients to bypass layers, and gradient clipping prevents exploiting gradients. These techniques are now standard in modern architectures. To summarize, the vanishing gradient problem is one of the biggest hurdles in training deep neural networks. It occurs when gradients shrink as they propagate backward, especially with sigmoid and tanh activations. The consequences are slow training, poor convergence, and failure to capture long term dependencies. Thankfully, modern techniques like rectified linear unit, better initialization, batch normalization, residual connections, and advanced architectures like LSTMs and GRUs have largely solved this issue. Understanding this problem helps us appreciate why deep learning evolved the way it did. Thank you.